됐나? 됐다. Today we will cover one of the most well-known AI model or framework in artificial intelligence, generative adversarial network, which can be called as GANs, as shown in here. And this lecture is based on the top-tier conference NeurIPS paper by Ian Goodfellow, which was published in 2014, which has been cited over 79 times as of 2025. And this high impact highlights how important GANs have become in the field of artificial intelligence. And let's begin our deep dive into the principle behind GANs, how they work, and why they matter on our research field. Let's begin by distinguishing between discriminative model and generative models. Formally speaking, as shown in here, discriminative model estimate the conditional probability Py by X, which is indicating that the probability of label Y given input data X. These kinds of formulations are used for classification tasks. In contrast, generative models estimate the joint probability Px, Y, or in the case of unlabeled data, we can just capture simply Px at the problem setting. This allows them to not only classify but also generate new samples. Informally, let's talk about informally. Discriminative model focus on telling categories apart, while generative models are able to generate new data that looks like the training data set. Also, the discriminative model cannot model Px and therefore cannot generate new samples from input data with input data, whereas generative models can do both. So they model the full data distribution and sample from it. And to understand the difference more clearly, we can look at what each models learn. Firstly, a discriminative model learns the decision boundary between the classes. In other words, it can draw the line that can separate classes like cat or dog or positive or negative. On the other hand, let's talk about the generative model. The generative model can learn the actual distribution of the data for each class. So it knows what dogs generally look like and what cats generally look like in the data space as shown here. To understand and as shown in here, interestingly, both type of models ultimately give us Py by X, Py by X for prediction, but they often learn it differently. Discriminative models estimate it directly, while the generative models often use Bayes rules to infer it from Px by Y and Py. But this is not any important. And let's talk about deeper discussion into the math behind these kinds of models. Discriminative classifier often learn Py by X directly. By using functions like logistic regression or neural networks. On the other hand, generative model classifier However, first estimate px by y and py. Then apply Bayes laws to compute py by x. This can give the generative models much more flexibility. They can classify just like discriminative models, but they can also generate data, something that becomes very important or becomes very essential when we move into GAN framework. Here we reinforce the key difference. Discriminative models can learn to draw the line, between classes. Generative models go further. They model how each class looks. For example, in images classification, a generative model can learn what horse and elephant typically look like in pixel space, pixel domain, and it can then generate new samples that resemble each class. This difference is fundamental when we design models for syntaxes like GAN framework. And this slide illustrates how generative models estimate the posterior using Bayes' theorem. For example, if we want to know the probability that an image is horse or coffee or some kinds of classes, we can compute this from the class conditional probabilities P x bar C1 or px bar C2 as well as the class priors. This framework shows us the benefit of generative models. They give a full understanding of how data and label are related, not just boundary between them. This is not. A key feature of generative models is their ability to sample data. Okay. From a learned distribution Px, we can generate new data points that resemble the training samples. This is essential in applications like image synthesis or star transform or kinds of data augmentation. It's also the foundation of what GANs are trying to do. Match the model distribution P model with the true data distribution P data. And the ultimate goal of generative modeling is for the model's output distribution, P model, mentioned in here, P model, to closely approximate the real data distributions as P data. When this happens, the generated data will look indistinguishable from the real data samples. In practice, this is very difficult to achieve, and GANs often offer one approach to get there. The challenging issue is to learn how to generate data points that are statistically similar to those we see in the real world, as shown in here, P data. Okay. This slide shows the structure of a typical GAN. The generator often takes in random noise, as shown in here, random noise G, and transform it into a data sample GZ. The discriminator often receive either real data or GZIT and output a probability that the sample is real or not. During for the network training, for the framework training, both network improve by competing or adversarial learning. The generator try to fool the discriminator, and the discriminator tries not to be fooled. Over time, as the training goes and goes and goes, this process improves both networks, ideally until the generated data is indistinguishable from real data. And let's focus now on how we train the discriminator here. In each training iteration, we feed some data into two types. We feed two types of data: real samples from the dataset and fake samples, which were produced by generator. The discriminator outputs a probability for each, ideally close to 1 for real data and close to 0 for fake ones, which were produced by generator. The discriminator's ultimate goal is to maximize its ability to correctly classify both types of data. We then use its feedback to train a generator, which we will talk about in the next slide. And let's turn to generator training. While the discriminator is trained to distinguish real or fake from fake, the generator is trained to do the opposite. It tries to generate samples that can fool the discriminator. In other words, G wants DGZ to be as close to 1 possible, which is meaning that the discriminator believes the generated sample is real. We alternate between updating D and G, gradually pushing G to produce more realistic data. So it's important to understand that G doesn't directly learn from the real data. It learns through the feedback process from the discriminator, D. These slides summarize the entire GAN framework. We have a generator that creates samples from random noise and a discriminator that evaluates whether samples are real or fake. The training data feeds into D and G generates its own samples from latent code G. The ultimate goal is to train both network in game-like setting. G is trained to fool the discriminator, and the D discriminator improves to detect fake data from G. By utilizing these kinds of adversarial learning process, we eventually reach a point where the generated samples become indistinguishable from real data. And let's talk about more theoretical view. If we fix the generator G, what would be the optimal for discriminator? Maybe this slide shows that the optimal dx for a given G is defined as the ratio of the real data density over the sum of real and generated densities. Mathematically, that means dx equal p data x over p data x plus p model x. This results is crucial because it can tell us what D should ideally output if it had perfect knowledge of the two distributions. Maybe this one? Maybe. Understanding this optimal discriminator helps us analyze the training dynamics of GAN framework. And here we formalize GAN as two-player min-max game as shown in here. And here, the discriminator aims to maximize the value function VDG, trying to correctly classify real or fake data. Meanwhile, the generator tries to minimize this same function, essentially attempting to generate data that maximize the discriminator's error. The equilibrium of this game is what we can call this the maybe Nash equilibrium, where neither player can improve their strategy without hurting themselves. This game theoretic perspective can give GAN framework their unique structure and behavior compared to the other neural networks. And this slide shows us the full mathematical expression for the GAN value function VDG. It includes two expectations. The first one is 1 over the real data distribution and 1 over the latent noise distribution. We want to maximize the log probability. We want to maximize the log probability that D assigns to real data and minimize log probability that D assigns to fake data. This formulation captures the adversarial dynamic. D wants to correctly classify and G wants to generate data that cause D to misclassify. This equation is the foundation for all gradient-based training in GANs. And we go deeper into mathematics again. We apply a change of variable technique to rewrite the probability density of generated data, PGX, in terms of latent variable G. This helps us relate the generator function GZ back to the output space X. So it's essential because for the network training, for the GAN framework training, we need to understand how changing G affects the output distribution. The generator effectively warp the latent space into the data space, shaping PGX to match PData X. Understanding this transformation is some kinds of key aspect to controlling how the generator learns well. Continuing from the last slide, we see the formula that express the generated data distribution PGX. 요거. In terms of transforming applying by G and the original latent distribution PGG, PGXG, This mathematical derivation is essential for computing gradients and understanding how updates G impacts the overall data distribution. This connection allows us to formally express the adversarial loss in terms of PGX, enabling the use of optimization technique to train the network. If you want to analyze this formula, please let me know. And with the optimal dx defined, after that, we now substitute it back into the value function VDG. The resulting expression shows us that the discriminator's job becomes finding this optimal decision function. When you plug in the optimal D, we can directly analyze how the generator's performance influences the overall training objective. We find that the optimal value of D increases when PGX becomes closer to P-data X. This insight leads us to more theoretical view of GAN convergence. To verify that the optimal D indeed gave us the maximum, we differentiate the value function with respect to D and confirm it that it's a maximum. This rigorous analysis shows that our formulation is stable under the assumption that D is optimal. In practical use, we alternate between optimizing D and G, so this theoretical stability helps us understand the convergence behavior. It also implies that the generator should push PGX to match P-data X as closely as possible to minimize these kinds of loss. And this is not important for you guys. And let's now rewrite the generator's loss more explicitly. The ultimate goal is to minimize the divergence between PG and P-data. This is expressed by using a combination of Kullback divergence, which can be called as KL divergence, which measure how one distribution diverges from the another. The formulation involves minimizing a function that penalizes difference between the generated and real data distribution This can help us understand that the generator is not just fooling D, it's it's actively aligning its output distribution with the real data distribution. So, this is not important for you guys, just looking at this slide, and we want to make same or similar distribution. And this slide presents us a very important theoretical result, a formal theorem regarding the convergence of GANs. The theorem states that this one, the global minimum of the GAN value function is achieved if and only if the distribution of the generator, PG, exactly matches the true data distribution, P data. At the point, the minimum value of the loss function becomes minus log of 4, because as shown in here and here, you can simply estimate the ultimate minimum of V is minus log of 4. Let's unpack what this means. Remember, GAN training involves solving a min-max optimization problem. The generator G is always trying to minimize the value function VDG, while the discriminator D is trying to maximize it. The theorem tells us that if the generator becomes perfect, which is meaning it generates data indistinguishable from the real data, then the discriminator has no power left to differentiate between real and fake. In this perfect scenario, dx becomes 1/2 everywhere, which is meaning it always guesses randomly. And when we substitute PG equal P data into our value function, as shown in the former slide, the optimal loss converges to minus log 4, which is approximately maybe minus 1.83 or 38, maybe minus 1.386 maybe. And this is the best possible outcome in the GAN setting. Both networks are in equilibrium, and the generated samples are as good as real. However, while this is theoretical goal, ultimate goal, in practice, reaching this state is extremely difficult and challenging. The challenges like mode collapse, vanishing gradients, and instability often prevents GANs from converging smoothly. Still, this theorem gives us some kinds of rigorous target to aim for and help guide the design of better training method and loss functions in GAN research. And again, we will look into how GAN are trained in practice. The GAN training process includes alternating updates between discriminator and the generator. Here we define the loss functions for both network. The discriminator aims to maximize the probability of assigning the correct label to both real and generated data. its objective function can be defined as shown in here and here. This means it wants the dx close to 1 and dgz close to 0. We update discriminator parameters using gradient ascent, as shown here. On the other hand, the generator's goals is to generate data that can fool the discriminator. So it minimizes these kinds of loss function using gradient descent, as shown in here. Using these kinds of updates are done in an alternating manner. Typically, we train D for one or more steps and then update G. This adversarial learning forms the key aspect or key aspect of GAN optimization. And in here, we re-emphasize the two key loss function in GAN training, but this is not any important for you guys. And this slide also visualize the update process first. The discriminator is updated using both real sample and generated samples. Then the generator is trained using the gradient coming from the discriminator's output. And the generator learns how to tweak its output to fool the discriminator much more effectively. The most important thing is that we do not update both network G and D simultaneously. Instead, we alternate their updates. Typically, we perform multiple D update for every G updates to ensure they stay strong enough to provide meaningful gradient. At the end of each round, we expect D to be slightly better at spotting fakes and G to be slightly better at hiding them. Over training time, this adversarial learning process ideally leads to high-quality data generation by utilizing G generator. And here we again visualize the training dynamics of GANs using a toy examples. Imagine G and D as curve moving within 1D or 2D data space. In figure A, the generator's output distribution is still far from the real data distribution. D can easily classify the samples correctly, and in figure B, D is trained to better distinguish real from fake, adjusting its decision boundary accordingly. And then in figure C, the generator updates its samples to push them closer toward region that D believes are real. And finally, the last figure, D, as training progress, if both networks are sufficiently powerful, G's output distribution aligns with the real data, as shown in here. Real data, at this point, D can no longer tell the difference and return just 0.5 for every sample. This And fourth process is what drives convergence in GANs and also what makes them so difficult to train in practice. And this slide shows also same concept with visualization of GAN training using 2D examples. But we will simply cover this slide. Here, Z space is mapped into X space through the generator G, and the discriminator D often learns to detect whether the samples are real or fake. As training proceeds, the generator is learning a complex transformation, one that contracts and expands different parts of the input space to match the target distribution. You can explore this process interactively through some kinds of